In the last video, we saw how we might find some of the most ideal hyperparameters for our random forest regressor. But we only set the number of, or in my case, you might have done this differently, you might have had some more time, but in the essence of time for recording these videos, I only set n iter to 2. However, in a previous experiment, aka step 6, I set n iter to 100 and found some more ideal hyperparameters than what we have here. So that's what we'll do. We're going to, in this video, train a model with the best hyperparameters. And we'll put a little note here. We'll go, note, these were found after 100 iterations of randomized search CV. And now, if you were to do something like this, like 100 iterations of randomized search CV, you still may find different hyperparameters, potentially better hyperparameters. The hyperparameter searching, or like finding the best hyperparameters for a model, is, as we've talked about before, it's not an exact science. It involves a lot of trial and error, a lot of experimentation. So for this one, you're just gonna have to kind of trust me that I've run this 100 iterations. It took a couple of hours on my Mac. So I'll just show you which ones we found. So most ideal hyperparameters. And that way, once we've gone through something like this, a randomized search CV to find some ideal hyperparameters, because this was only, I'm scrolling back and forth here, because this was only trained on 10,000 examples, what you'll probably do is use randomized search CV to find some ideal hyperparameters across a space like this on a subset, because otherwise it would take hours and hours and hours, and then retrain a model on the full data set, which is what we're about to do now, with the most ideal hyperparameters that were found in randomized search CV. So let's call this one ideal model, and we'll set it up here. Random forest regressor. So in my case, n estimators was 40. Now this is interesting, right? Because the default in random forest regressor, if we go here, Shift Tab, the default is 100. So it's actually, from the randomized search CV, it's actually found that 100 estimators weren't required. So 40 still provides pretty good results. Min samples leaf was found to be 1. And then min samples split was found to be 14. And then max features was found to be 0.5. And n jobs, of course, we're going to set to -1 because we want our computer to use all of the processes that it has. Well, in my case, I do. Max samples equals none because why? We want to train on all of the data. So we set max samples to none, aka it will train on as many samples as possible. And now we're going to fit the ideal model because we've just instantiated above. Ideal model dot fit on the training data, xtrain, ytrain. And now this may take a couple of minutes. So what we'll do, I'll run this cell. And again, we're going to time travel. And once the training is complete, we'll be able to see how long it took because we've got time. And then we'll evaluate our model. Beautiful. So that took about 1 minute and 14 seconds. Now that's on the entire data. And the reason being is, probably the main reason is because n estimators is 40 rather than 100. So what that means is the random forest is building 40 smaller little models rather than 100. So almost, 2.5 times less. And I did forget one parameter that we probably should have put in here. Random state equals 42. I'm not going to rerun the model now, but just so it's there, I'll put a little comment here. Random state. So this is so if we were to set a numpy random seed, same thing. Random state, so our results are reproducible. Is that how you spell reproducible? Yes, it is. Beautiful. So if I was to run this cell again over and over and over with random state set to 42, we would get the same model being fit. But that took about 1 minute, 14 seconds on my computer. It may take a little bit longer, a little bit shorter on your computer, depending on how much processing power you have. And if you're running randomized search CV a number of times more than what we've done up here, you may potentially find different parameters to what I've found here. And if you have, I encourage you to share them so other people can try them out, and we'll evaluate it to see how they go, to see whose parameters are the real best ones. So let's check it out with our handy show scores function, and we'll pass it our model that we just trained. Shift and enter there. Beautiful. And because this is trained on all the data, we should see a significant improvement over the model that we trained before. So let's go up. Here we go, RS model. Okay, what we might do is bring these closer to each other. So we can go scores for ideal model, trained on all the data. And let's go here, scores on RS model, only trained on 10,000 examples. The exact same line of code, we ran a couple of cells up. I'm just doing it here so we can directly compare them. All right, so let's look at here. The valid RMSLE is probably the one we want to pay most attention to. As you can see with our ideal model, in 1 minute, 14 seconds of training time, it's gone through 400 or so thousand rows and reduced the valid RMSLE, yep, far out, that's a mouthful, by, what is it, about 0.8. So that's pretty damn good. And if we saw with this, we were already doing well on the Kaggle competition with our original model. Let's see where our new and improved one, which is our ideal model. So we're looking at this here. Valid root mean square log error, 0.246. Where does that get us on the leaderboard? 0.246. All right, so around about there, so 30. So we're almost in the top 30 on the Kaggle leaderboard, just in a model that took a minute to run. And going through here, we're like, this is a random forest regressor straight out of scikit-learn. That's pretty damn impressive, and we haven't really done an incredible amount of data manipulation. We've turned our data into numbers, we've filled missing value, but we're already getting some incredible results. So what we'll probably do is leave our ideal model there. We could search for longer with randomized search CV up here and find some better hyperparameters and probably slightly improve our model even more, maybe push us right into the top 25. That'd be pretty cool. But what we might do now is see how we'd make a submission to Kaggle. So what does this mean? So if we come here, how do you even get on the leaderboard? Well, if we go here to data, to get on the leaderboard, we have to make some predictions on test.csv. So right now, our predictions are on valid.csv, but all of these scores on the leaderboard, so really we are just guesstimating where we'd end up because we're predicting on valid CSV at the moment. We're evaluating our model on a validation set. But if we come back to overview and evaluation, what we have to do is submit a submission file. So, okay, submission file should be formatted as follows: sales ID, sale price. So that's what we probably might do now. We might import the test data set and format it in a way so we can use our machine learning model on it and create an example submission in the format that Kaggle is asking of us. So that sounds like a good plan. Now we've got an ideal model. We'll use that to make predictions on the test data set.